Thanks, Marcel. Yeah, as Marcel said, I'm Johan. I'm part of the group here in Gothenburg with Marcel and Sebastian Swart, for example. And I'm about to present what will be chapter 2 in my PhD thesis about the sensible heat flux variability in the Southern Ocean. So we're going to go on a little tour, and I'm going to show you quite a lot of cool stuff. And this is work that has been ongoing for the last year or so, for me, and then previously with another PhD student. Just see that it works. As Marcel said, I'm going to talk about USVs, so in this case sail drones, and how they can help us validate reanalysis products in a remote region. Also take a look at synoptic winds and see how variability can be associated to wind direction, for example, and also have a look at some sampling scales, which these high-resolution data sets can tell us a lot about. And finally, we're going to end on the importance of submesoscale fronts. But firstly, I just want to say that as of last week, I woke up to news on Monday saying that this work is accepted, which is a relief, especially to receive on a Monday morning. And I just wanted to share that with you. So it'll be out in a week or two, probably. But getting into it, what do we know about the climate? Well, the world is burning. 2024 was the warmest year on record, and 2025 is looking like we're heading into another record year. And we do know that this heat mostly ends up in the ocean, where about 90% of anthropogenic heat is taken up. And from model studies from Richard Williams, for example, last year, we know that a lot of this is, or the majority is taken up in the Southern Ocean. But there's a lot of stuff that we don't really know about the variability of this in the Southern Ocean. But some of the things that we do know, for example, there's a paper by Matt Maslow in 2018 where they looked at high-frequency QNets, so features or processes that occur on less than 90-day timescales, and found that they account for about 1/3 of the total variance. And that the decorrelation length scales ranged from about 1,300 kilometers zonally and 500 to 900 meridionally. And this work was then furthered on by Channing Prend earlier this year, where they kept looking at the high-frequency 90-day QNet and saw that it was highly regional and seasonal in the variability, and that this was mostly driven by synoptic storms and mesoscale eddies. And they also found that decorrelation scales are about 100 kilometers in energetic regions, like the boundary currents, within the ACC or the Agulhas or the Malvinas Confluence, for example, and about a 2-day decorrelation scale across most of the Southern Ocean. Maslow used a 3-day model output, and Channing Prend used a 1-day reanalysis. So these are still models, but what do we know about the observations? Well, in terms of when it comes to sensible heat flux, to be honest, not a lot, because we don't have that much observations to tell. Most of the Southern Ocean, we have about 100 daily observations per 1 degree. And this is for the entirety of the record. So it's really, really undersampled. But over the last couple of years, or the last decade or so, there's been evolvement. So we've gone from, not just having ships of opportunity or like cruises, TSG, etc. But there's this new platform called USVs that I think we're all aware of, but I just wanted to highlight it again to show a few different of these. And this is part of a work that we did earlier this year with Ruth Patterson, for example, and Oasis, where I made this map and collected all the USV data that we could find from 2011 up until 2024. And one of these data sets is the one that I'm going to talk about today, or rather 3. We had 3 sail drones circumnavigating Antarctica in 2019. And this is 1-minute data, so it's super high resolution in a very, very undersampled region. So this can tell us a lot about processes that occur there. And I want to start with just talking about the data sets, and I'm going to show you here, which is a plot of the South Pacific sector of the Southern Ocean. And you might wonder why I only show you this data. Well, it's because after the Drake's passage, actually all three platforms lost data, so that we couldn't calculate sensible heat flux, for example. And we think that this is due to icebergs, but we can't rule out other terms or other sources of interference. But anyway, they were deployed off of New Zealand in austral summer and in austral winter. So it gives us a couple of months of really good data in this sector. So what does the data look like? It's quite variable, at least when it comes to wind speed, and it's also very, very windy, which, if you look at the deployment period and to have a mean wind speed above 10 meters per second, that is quite windy, but it is the Southern Ocean, so we're all aware of that. When it comes to the air-sea temperature difference, we can also tell that it's mostly negative, meaning that the sea surface temperature is warmer than the air. So the ocean is largely losing heat, which is reflected in the sensible heat flux. Something that stuck out to me was when I looked at the SST, I saw that it was colder for summer, which piqued my interest. And that also shows up here when we look at the mean. Now, there is the meridional gradient to take into account, because the summer data set went further south. It was in the ACC. But this also gives us an opportunity to actually look at the different regions. So we're comparing the subantarctic zone with the Antarctic syncopolar current. And here's a little bit of what the data can show us. So we can see that the SAS is actually windier than the ACC, which is probably due to storm tracks and how they are evolved. And that the ACC is slightly less windy during winter, which I find quite interesting. When it comes to air temperature and sea surface temperatures, we see that indeed SAS is warmer than ACC, which is expected. And that is also reflected in, obviously, the temperature difference. What's interesting, though, is it seems like we have a stronger gradient in the SAS than we have in the ACC, which is reflected in the sensible heat flux. That is slightly more negative, and it looks like we have more large negative values. So what is the first piece of the puzzle that I'm trying to lay here today? Well, it's that driven by larger air-sea temperature gradients, the subantarctic zone exhibits greater ocean to atmosphere heat loss during winter compared to the ACC, which is a good piece of vital information that we can have. When it comes to this region, again, I want to highlight the lack of observations and therefore a lack of reanalysis validation, which is something that we can do when we have these data sets. And what I'm showing here is for wind speed, air temperatures, SST, and sensible heat flux. The wind speed and air temperature is height corrected to match the RF5 10 and 2 meters. And sensible heat flux is an average over an hour instead of a snapshot as the other three. What we can see here is overall a very good agreement between all four data sets, and also the typical underestimation of high wind speeds that we have seen in RF5 in a lot of previous studies. And I think this is because of like subgrid variability that really isn't captured within the 25-degree grid cell of RF5. And this is also reflected in why the spread for sensible heat flux is slightly larger than the other components. So this gives us another piece in this region, and that the USV data provides us with valuable validation for RF5 in a very data sparse region, and we find both agreement and some areas for refinement. Now, if we go into our synoptic winds, which I think is one of the reasons why we have this variability, we can lean on, or I've leaned on, two studies from Sarah Ogul in 2018 and from Veronica Tamsit in 2020, who used mooring data to look at wind direction and the strength of turbulent heat fluxes. And there was a correlation between kind of southerly winds and extreme heat loss events. So meaning that as storms roll by, they advect cold polar air northward. And therefore it takes cold air over warmer and warmer sea surface temperatures, which then increase the gradient, which will increase the turbulent heat flux. But since we have these data sets across this entire region, we can also do the same analysis. And this is exactly what we find, that there is a wind directional dependency with winds, with extreme heat loss events, with sensible heat flux, that when winds are coming from the south, storms affect the cold polar air more northward. But we also see in this data, especially in summer and in the ACC, is that there's a component of actually what looks like heating, so that we have warm air coming from the north going over then colder temperatures in the ACC, which then the ocean takes up heat, which is also quite interesting. So we find that the large heat loss events are driven by advection of cold polar air, and there's some positive anomalies associated with warm air from the north. Another piece of the puzzle. Now we go into a little bit of scales, of sampling scales. So as I showed you earlier, Channing looked at the high frequency QNet and found decorrelation scales of around 2 days across most of the Southern Ocean. And this is consistent with synoptic storm variability. Now taking the previous analysis into account, and also thinking about these 2 days, we thought that it could be quite interesting to use these high resolution observations to actually look at 2-day autocorrelation intervals. So splitting all the data up in 2 days and doing an autocorrelation function on that data. What we then find is that we see decorrelation scales. So here I'm showing you for the mean of all the intervals and one standard deviation. And we find that the decorrelation scale for sensible heat flux is around 10 hours temporally and 50 kilometers spatially. And this is what I would refer to as like event scale variability. So the correlation that is associated with that. Now, as I said, event scale sensible heat flux decorrelates at characteristic scales of around 10 hours and 50 kilometers, which is a quite important puzzle piece to have. Now, when we go into a sampling scale uncertainty, we can think of, well, how does this actually affect our, if you have for example, what Matt was suggesting in 2018 was to have an array of sampling floats, for example. So how does this event scale affect the larger scale uncertainty? So by using the high resolution data again, we can progressively average it to simulate coarser and coarser sampling scales. And what we see here is a linear increase of the spread, meaning that the measurements are actually somewhat correlated in time, meaning that it's treated like red noise instead of white noise. White noise, we would have seen a logarithmic increase, which we do not. What is very nice here is that we start at 1 minute and then go up to 1 day. And if we use the decorrelation scales we found in the previous exercise, we can see that the uncertainty, which is what I'm defining here as the difference between the 5th and the 95th percentile spread, so essentially this distance here as we increase, is around 3. It's around 2.5 for 10 hours, and for the spatial component, which I'm not showing you here, but it looks pretty much the same. Trust me, it's in the paper, you'll see it later. It's around 3 watts per square meter at the event scales of 10 hours and about 50 kilometers. So sampling at the scale of these physical events captures the signal with a measurement uncertainty of around 3 watts per square meter, or plus minus 1.5 watts per square meter, which I would say is very, very good. It's around the uncertainty that we want to reach with future products. And then for the last piece of this analysis, it's turning me into submesoscale fronts, which I'll try to walk you through slowly, but we start with our space series. So I essentially take our 1 minute resolution data and then bin it into 200 meter resolution data set. And then we take a look at SST and more specifically SST gradient. And I define a front to be an SST gradient that is greater than 0.0125 degrees Celsius per kilometer, and that this has to occur for 3 consecutive observations of the same sign in SST gradient. And that's what I'm showing you here, just a snapshot of a couple of different fronts that we found in the data set. What I then want to do is we want to figure out how much comes from the ocean and how much is attributed to the atmosphere when it comes to changes in sensible heat flux over these fronts. What we do then is we detect, or we calculate, the absolute change of properties from start to end. So we look at wind speed or air temperature, for example, and then we look at the values at the start and at the end of the front and take the absolute change over that. And if that is higher than a certain threshold, it will be classified as uniform, meaning that the atmosphere really doesn't change over the front, or dynamic, meaning that it does have some type of change. And doing that allows us to classify them in different ways. So we used 0.5 meters per second winds and about 0.2 degrees of air temperature. And this gives us it gives us two data sets of uniform and dynamic. And when we look at all the fronts in all of the data sets, the three combined data sets, we found over 8,000 fronts ranging from about 800 meters, I think, to 30 kilometers was the longest front. And we found an even split between uniform and dynamic. There's slightly more dynamic, larger fronts, which I don't think is surprising, because the atmosphere tends to decorrelate faster, as we've seen. Then we go into just plotting the data up here. We can see in the top two panels to the right, plotted the absolute change of SST and sensible heat flux as a function of front width for both uniform and dynamic conditions, and also fitted a linear regression to these lines. And unsurprisingly, I can determine that SST is what drives the sensible heat flux during uniform conditions. This is kind of also an artifact of the fact that we are basing the front finding criteria on SST. What we also see is that wind speed is dominating during the dynamic conditions. So it's the change or the variability of wind speed that sets the sensible heat flux. For the bottom plot, I've box plots for sensible heat flux. So essentially taking the top right plot and then just making box plots of it so that we can get a better grasp of how the data evolves. And we can see that the small scale fronts, so the sub-kilometers, are really, really variable. In some instances, there are 80 watts per square meter per kilometer, which is a very large gradient. But over the uniform conditions, we see that, well, the SST is actually causing a rather stable gradient across front width. So there's no change in the gradient as you increase frontal width. And these gradients that I mentioned, they align with previous studies, what we've seen in literature. I haven't shown you air temperature here, but it's around 4 degrees per 100 kilometers. SST is around 10 degrees per 100 kilometers, and sensible heat flux is around 150 watts per square meter per 100 kilometer. And we also see that because of the pure number of small fronts, that they have a leading order contribution to sensible heat flux variability. I think I don't remember exactly, but it's on the order of a factor of 2. So the fronts that are smaller than 1 kilometer cumulatively affect sensible heat flux about twice as much as those that are larger than 4. And that's what it basically says here, and that is the kind of the last piece of this puzzle that we have here, that there is an abundance of small-scale fronts, and they contribute more to sensible heat flux variability than larger fronts. However, it's the wind speed that is driving this variability of the small-scale fronts, and it's more SST which is driving the variability in sensible heat flux in the larger fronts. And that is the work that I have today. So we've looked at reanalysis and found that they match pretty well. We also saw the wind dependence of synoptic winds, both with cold polar air and warm air from equatorwards. We found a bunch of sampling scales to take into account, and we also investigated the submesoscale fronts and the importance of actually measuring these, which probably have a bigger effect locally than basin-wide scales, as we see that the sampling scales are around 10 hours and 50 kilometers. The final thing I want to mention quickly is this initiative that we have gotten endorsed by Goose, which is called Sunfleet, which is part of a paper that we did earlier this year. And here's some words from Ruth Patterson, who's driving this excellently. And that will coordinate a global effort with the outcomes greater than sum of all the individual parts. And that the Sunfleet will allow us to transcend traditional siloed approaches to data delivery. And this will benefit both industry and humankind. And also a word from Megan Cronin, which says that the true value of these USVs are improving forecasts will come when their data from coastal regions to the remotest regions of the global ocean can be fed into operational models within minutes of being captured. So they really can improve all the systems, and that's where part of this work comes into play, I think. And I realized that I've talked at you for a bit, probably quicker than I thought that I would, but I think I'm getting ready to take some questions if you have them.
Great. Fantastic. Thanks, Johan. That's super. Does anybody have any questions? If you do, they're welcome to unmute yourself and ask. Lily.
Hi, Johan. Thanks for this work and congratulations on getting it submitted. It's really fantastic. I'm just going to be honest. I missed the definition of the dynamic versus uniform fronts. Do you mind going over that again for me, just so I can develop a better question?
Yeah, so it's essentially taking the value at the start and at the end of every front. And then we're checking if in this case, wind speed, if it's above 0.5 meters per second, or the difference. And if either of wind speed or air temperature is above this limit, then the front is classified as being dynamic. So if there's not a change more than 0.5 meters per second or 0.2 degrees Celsius, then we say that it's basically uniform. If that makes sense.
And is there work that motivated you to look at these differences, as in why some of these fronts, why we might care about this classification?
I think it was, from my side, it was more to figure out a way of how to isolate the oceans, the sort of the, how do I call it, how much the ocean is driving, or the SST is driving the change in sensible heat flux.
Gotcha.
Rather than focusing on uniform and dynamic, it's just to try and isolate as much as possible.
Okay, so it's kind of a first pass at separating out a potentially atmospheric driven signal versus a sea surface temperature driven. That's okay. Gotcha. Thank you. I appreciate that.
Thanks.
Oh, hi, Johan. I think this is really cool. Thanks for sharing this with us. I guess this probably ties in with Lily's question, because I guess your decorrelation timescale is really interesting because it's super short, right? And so I was wondering if there's a way to, because you've got two things going on. You've got the storm that's propagating quite quickly, but then you've also got your slower unmanned vehicle, which is propagating, or which is moving more slowly, but across these submesoscale fronts. Is there a way to kind of quantify how much of that decorrelation timescale is coming from the differences in your Lagrangian signals? And then my second question was if you had thought about like how often your southerly winds were coming from like different sorts of systems. Like this is something that I think is really interesting. Like I'm not I'm still trying to figure out how storms evolve and like cyclogenesis and that sort of thing. And there's got to be some differences between like it being in the wave phase versus the completely cyclonic phase. And I was just wondering if you guys had thought at all about that with your work.
Yeah, no, hi, Catherine. For the first question regarding the quasi-Lagrangian aspects of this study, it's something that we have discussed a lot, both internally, internally for myself, with myself, and with my co-authors for this study and the reviewers. And it's something that is really, really difficult to disentangle. Because as you say, we're kind of the USV is moving across the ocean, but the weather is moving across the USV. So it's very difficult to disentangle those two with the way that these data sets were collected. If we have a kind of a station keeping USV, that would be different, which is something that we can look into the future for future deployments. But at the moment, we're kind of saying that it's a mix of both, and with this data, it's too difficult to disentangle. We did see a slight correlation between vehicle speed and decorrelation length scales. So essentially that when you have stronger winds or when you're traveling faster, we tended to see slightly longer decorrelation scales because you're covering a longer distance. And regarding to the second question, it is something that I'm quite interested in for going forward, but it's not something that we have looked into. I want to incorporate a lot of this work into my future chapters in the PhD, to think about connections with storms across circumpolarly and where are they coming from and how are they developing, and that type of thing. But that is work to be done, but I'm still very interested about it. So thanks for those points.
Okay, cool. I have a third question. Sorry. I don't know very much about the variables that you get from these sail drone experiments, but is there a way to get latent heat fluxes as well, or like an estimate of that, or are you pretty stuck with sensible?
No, we can absolutely get latent as well. The reason
Awesome.
why we didn't is because for one of them, we didn't have. So I think it worked for a couple of weeks, and then it was just saturated at 100% humidity, which I don't think is true. Therefore, we decided to, well, okay, it is what it is, and we're only going to look at sensible for this case. But absolutely, they carry they carry humidity sensors, which helps us get latent heat. A lot of them nowadays also come with radiometers, so that we can get a full heat budget, which is really cool.
Okay, great. Thank you.
Pleasure.
All right, we have, Sarah. Oh, two
Yeah.
Sarahs. Okay, so can you go first?
Well, I'll just ask a quick question. Now that you've done this work, what do you see as the priorities for a next iteration of autonomous sensors in the Southern Ocean? What would the deployment priorities be? What would you want to measure?
Oof. That's a nice question. But I think it's absolutely, as I was saying, just getting a full heat budget is quite important, and possibly trying to go from what I've shown here is bulk fluxes, and if we can get eddy covariance on these USVs, I think that is more akin to the actual true flux, even though bulk gets us really, really close. And I think that's one way that we would go forward.
Thanks.
Hi, I have a quick question. But first, this was really cool work. I did kind of a similar analysis in the Gulf Stream, but it's really cool to see this seen to completion. Mine is unpublished, but I wanted to ask, so you said there was 8,000 fronts detected in your data set, and I wanted to make sure I understand the dynamic front categorization. I was curious if the interpretation is that there's a storm moving over at the same time that the sail drone is crossing an SST front, or if you're saying that the presence of the SST front is accelerating the winds and changing the air temperature.
That is something that we thought about, or that was one of the things I think that led into it, from Shelton studies in 2004, for example, and things like that. But that is not what we're saying here. We're simply trying to distinguish two types of data sets, or two criteria, so that we can try to get to the ocean's role in the sensible heat flux, rather than seeing if SST is affecting air temperature or wind speed. But that is absolutely work that can be done with these platforms, I think. And the high resolution nature of them is super valuable and something that should be looked into.
Thank you.
Yeah, Lily.
Hi, thanks again. You've hit on a curiosity spiral for me. So as you know, Johan, temperature gradients in the ocean are really important, but there's a big salinity gradient as well, kind of especially north-south of the polar front. I'm wondering if I know there are less implications in terms of air sea fluxes, but for those of us who care about subsurface processes, have you looked at sea surface salinity fronts? And is that something that you are able to do with these measurements?
It is not something that we have looked into, no, for this, because we're focused on heat generally. There was a moment, I think, early on in the process when we tried to look at density fronts, where salinity would come into play, but then it would be, okay, well, what part comes from temperature, what part comes from salinity? And then we decided to just purely look at temperature fronts. But it's absolutely possible. I mean, we have SSS sensors on them, so it's absolutely possible in the same way to do.
Yeah, I asked because measuring sea surface salinity from space is really difficult, right? And so those kinds of measurements are really valuable to get at those density fronts, and density being the thing we, deeply care about, at least on the ocean side. And so if you ever do want to think more on that direction, let me know, because that is really exciting to me.
Sure thing. Yeah, it's a great opportunity, I think. But there's salinity is difficult to measure in the field as well from these, because they're so close to the surface and it's conductivity cells. So if you get bubbles, for example, down in the water, then you get a lot of spikes. And then it's a matter of, okay, how much is an actual spike and how much is a true signal, which is surprisingly more difficult to do if you have a higher resolution than lower resolution.
I totally believe you. I know you've worked with gliders too, and yeah, there's a lot of art rather than science that goes into salinity sometimes.
Yeah, so Johan, I can ask a quick one. I was quite interested by when you were showing the heat flux the sensible heat flux as a function of the wind direction. Most of the heat loss comes from winds coming from the south, and you show this as this element of heat gain, right? And this kind of helps me answer my question, because I was wondering about seasonality with this. And one question is there seasonality? And I can kind of see that a little bit now. But the other question is, this is the Pacific, and do you expect that this might be different if we look at sort of interbasin comparisons, and how this might affect, I guess, ocean warming in these regions?
Yeah, it's a good point, and I think it will likely have. I think it might look different in different basins, maybe as a result of the change in for example, SSD gradient, so the meridional, I hate that word, gradient, which is different in the Pacific than in the Atlantic, for example. But there's also differences that this is an area of mainly heat loss, but I think in the Atlantic, the ocean mostly gains heat. So I think in the Atlantic, we would maybe see a stronger association with winds from the north or northwest, coming from, if you have warm, humid air coming off of South America, for example, that would play a bigger part over the South Atlantic. Seasonality to be explored. And it's something that I want to look into going forward.
Sarah.
Sorry, I have one more question. You did this comparison between the sail drone observations and the reanalysis. I was curious if you estimated what kind of uncertainty or bias there would be if you kind of, used the reanalysis data throughout your analysis. Would there be as many front detections? Would there be fewer because that underestimates the wind speed and it wouldn't meet your criteria? I was wondering if you thought about that, because something that we do as oceanographers is, blend a combination of in situ and reanalysis when observations are not available. And so I think you make a strong point that co-located observations are really important for this type of work. And I just wasn't sure if you kind of propagated that through to quantify how much.
Yeah, no, that is something that I thought of, at least when I was reading your papers. But I think it's in this case comparing the high resolution data set that we do have, which is 1 minute, and it means that we can get down to 200-meter resolution in space, which the 25-kilometer Era 5 not really will be sufficient to capture the small scale fronts that we're looking for. Therefore, I think it stopped quite early on in the thought process. But it's a really good point, nice point to do. Sometimes we might use, for example, if the wind speed sensor breaks, then you might use Era 5 wind speeds, but in situ USV data, for example.
Great. Any other questions? Okay. Well then, one final time, thanks again, Johan. Splendid work and a great presentation. I appreciate the time and effort that goes into this.
Thank you.
Yeah, so that's all for today. There is another webinar next month. I have just forgotten, but it's on the 23rd of October, I believe. The message will come through on the SOFLUX next newsletter, so you'll see all the details there. But be sure to sign up, and thanks for joining us today. Thanks, Johan.
Thank you.